All right, good afternoon, everyone, and welcome to our Snow Melting Solutions webinar. I'm your host, Greg Jackman, the Specification Program Specialist here at Watts. Today's webinar is the next installment in our series of webinars geared specifically for you guys, our engineer, architect, and specifier customers. Just to give you a little background on this series, we hold several webinars throughout the year that cover a variety of topics. Our presenters are our in-house technology and product experts. And thanks to our partnership with the American Society of Plumbing Engineers, ASPE, we're able to provide you with 0.1 Continuing Education Unit, CEU, credit if you stick around for the entire webinar. After today, our next one will be on August 28th, where we'll be talking about Legionella and smart and safe hot water solutions. If you're interested in registering for that, please keep your eye out for our emails, or you can reach out to me directly at gregory.jackman@wattswater.com, and I'll sign you right up. So with that being said, I'd like to introduce you to the presenter of today's webinar, Colin Marshall, our Systems Engineering Manager at Watts. Colin's been active in the hydronic radiant market since 1995. During this time, he's authored the technical manual, Understanding Radiant Systems for RSES. During the duration of Colin's presentation today, the phone lines will be muted, but we encourage you to submit questions via the chat window. Just hover over the chat icon at the bottom of the WebEx and type in your questions here. We'll then address them during and after the presentation. So with that, let me pass it off to Colin to get started.
Thanks, Greg. A couple things. I just want to take time here and just thank everybody for showing up. We appreciate your interest in snow melting applications. It is truly one of those areas that we feel is greatly expanding. People have garnered a great interest in snow melting systems here in the last several years for various reasons. Some of those reasons we'll touch on here in the next few minutes. So some housekeeping rules here. This is an ASPE CEU credits only. It has not been approved by the PDHs or for PEs. And some other tidbits here that you can kind of read through. So a couple other things here, a couple of highlights. We're going to go over some reasons to consider a snow melting solution, some financial impacts on both operational and installation, some various control considerations, assortment of mechanical solutions, and some other things that you may or may not have questions on. And I encourage everybody to take a few moments to kind of jot down some questions as you go through, and please ask them as you think of them. There's a chat window provided. Just type them in, and we'll get to those questions as they pop up. We'll take a few minutes and go through those. We're also going to try a couple things new for this presentation. We'll have a couple of polls that we'll throw up throughout the presentation just to kind of spark some interest and kind of get some thoughts going, trying to see where everybody is relative to some background information and current understanding of snow melt systems, and that kind of help guide us a little bit along the way as well. So poll number one, and Greg's going to throw that poll up here for us. There we go. So how many snow melt projects have you been involved in? We'll give about 25, 30 seconds for everybody to answer this. Okay, we'll give it about 5 more seconds, and then we'll kind of close this down. All right. Poll has ended. Let's see what the results are. Let's see where everybody sits. Maybe.
I'm just getting those results up right now. Hold on one second.
Okay. So bear with us. This is the first time we're doing polls, so we may have some technical glitches. All right, here we go. All right, looks like the majority of us have done at least a few snowmelt systems, so that's good. For those of you that have not, it's a great opportunity to kind of branch out and try something new. Hopefully the presentation we'll give you today will give you some information on where to start, some good questions to ask, and some good starting points to drive that interest a little bit. All right. Let me close that. So where do we want to look at using snow melt systems? To be real honest, anywhere that it snows is a good location for a snow melt system. Beyond that, what should we look for? Really, we're looking at things that we're customers and applications and trying to understand where the benefits are for our customers. And depending upon who the customer is or what the application is or even what the industry is, those needs and wants and those target performance is going to change. And sometimes it's going to be a convenience factor. Sometimes it may actually be more of a liability issue, both for them as a business and for potential customers that are walking across or using a surfaced area. So if you're doing a parking garage, for example, the interest may not be to snow melt the entire parking garage, but just the entrance ramps, because those are the danger areas where people are entering and exiting the parking garage. Those are the areas where traction or loss of traction really drive the greatest impact. It could be a car wash where it may not be snowing. It may not be, the driving factor may not be actual snow removal per se, but more of preventing ice buildup. As cars leave a car wash, the apron areas where they pause before they enter onto the roadway, water drips off the cars and has the potential to freeze on that apron. The next car that comes out hits an icy spot and no longer can stop before they enter the roadway. And so you have a liability, you have a hazard that you're trying to eliminate, not so much from a snow removal perspective per se, but ice prevention. So helipads. Depending upon the application of the helipad, it could be a hospital helipad where the helipad is located 4 or 5, 10 stories above the ground. One aspect is going to be, hey, convenience for the trauma unit and team as they transport patients from the helicopter into the building. Obviously, you want to have a nice clear surface for them to walk on. You don't want to have anybody slipping in that environment. The other aspect of that is to the helicopter itself. You want to eliminate as much of the debris on the rooftop as possible to prevent damage to the helicopter, as that downwash from the rotors when they land and take off has the potential to kick up debris that can be hazardous to the helicopter itself. Beyond that, from a helicopter or a helipad standpoint, you have people on the walkways below, on the ground level, 10, 15 stories below. As debris can be kicked up, it can be kicked over the edge of the building, and that creates a hazard for people down on the ground. So there's a lot of different motivators and drivers for various applications. We can also look at residential and light commercial or retail applications. You know, in these applications, you're dealing with, maybe it's a convenience aspect. You want to have clear ways so patrons have the ability to get into your shop easier. If we're looking at hotels, I can't tell you how many times I've gone to a hotel and they will just dump the walkway out front with salt. And as you walk into the hotel for 15 or 20 feet over brand new carpet or tile or any number of floor coverings, it's just salt laden. And that is not only a hazard from the standpoint of bringing in chemicals into an environment you don't want those type of chemicals, but it degrades the integrity of the floor covering itself. So there's a lot of reasons to do snow melting for car wash or for hotels. You can also look at grocery stores. We can do the same thing for grocery stores. Clear that walkway as people enter and exit the grocery store. What else we have here is our tidbits.
Drive-throughs for convenience stores and, coffee shops and stuff like that.
Yeah, coffee shops. Anything with a drive-through is a good area for that as well. Chemical damage and concerns. This is for not only interior space, but it can also be for your driveway material itself, the concrete, brick pavers. It could be different kinds of stone that as you throw chemicals out onto those areas to remove ice and snow, you're actually damaging those surfaces as well. And these are typically areas that are investments. These are surfaces that you want to preserve and extend the longevity of them, and snowmelt systems help do that. There are some areas where you can be looking at a snowmelt system from the safety of others around you, in the sense that in certain areas, if your incline of a driveway or a motorway is beyond a certain percentage of grade, you're required to do a snowmelt system, because you need to ensure that that incline is free of snow and ice so that you don't have a hazard to somebody else. Some areas require you to have a snowmelt system that is compatible with the environment. You can have areas that have requirements that if you live within so many yards of a waterway or a runoff area, you cannot do chemical snow removal. You have to have some other means to remove snow. You can also have areas where physically getting to spaces to do bladed snow removal may be an issue. You just can't get in there effectively to remove snow, or have any place to put the snow once you've removed it from the area.
I was going to say landscaped areas that are adjacent to driveways. You know, if you get salt that runs off into those, it'll kill the landscaping, and so that's another reason to do that.
Absolutely. Thanks, Tracy. So there's a lot of reasons that drive people to look at snowmelt systems. Retail areas are always a good area. Stairs, anything that has stairs where people are walking, good area for a snowmelt system. That is a very high hazard area for a trip and slip type of situation. Dining areas, patios, these are great areas for snowmelt and snow removal. If you want to extend the exterior use of a restaurant, like the shown ski lodge up there, these systems can also have dual use to some degree. Patio systems that are designed to do snow melting may also be able to be designed to extend comfort seasons into the fall and spring months as well, so that you enhance the exterior dining, not from a snowmelt removal standpoint, but just overall cut the chill, so to speak. So snowmelt systems can have a dual use in that sense. We kind of already touched on this. We're looking at preserving the actual surface area itself, preventing the use of salt and other equipment or other chemicals to remove snow and ice. Okay, we have another poll that we'd like to look at. Greg's going to throw this up here and we'll see what we have. We have, what industries are requesting snowmelt solutions? What are you seeing as the biggest driver in your area for a snowmelt solution? We'll give you about 30 seconds here to kind of respond to this. All right, we'll give about 5 seconds and we'll lock this down. Okay, it has closed. Let's see what the results are. Healthcare seems to have won this one. And that's probably one of the drivers right now. That's the industry that we're seeing the biggest activity on, healthcare and hospitality, but really healthcare. And there's a lot of different reasons for that, I believe. Helipads are a big driver for healthcare. And then you're also looking at, yes.
We had a question come through right now. Where do you place schools in this poll?
Schools are on the list. We see a lot of activity with schools from a radiant aspect, for sure. Interior heating, we see a lot of school projects, especially for like preschool ages, classrooms where children will be on the floor a lot. We see a lot of those for sure. Snowmelt, ironically, we haven't seen a lot of snowmelt systems on schools. And I'm not really sure why. Some of that, I believe, is, just cost of systems. I mean, we're dealing with an industry that kind of is pressed for dollars a lot of times, and that may or may not be one of those areas that they're able to actually financially budget for. But it would be an ideal place to see them. Where we do see more snowmelts is in the college area. We're seeing more and more snowmelts show up on the collegiate level as opposed to a K through 12 standpoint. And obviously in that area, in the collegiate area, you definitely have more people that are walking. Large areas, primary transportation is either walking or bicycles. And those are areas that take a lot of time to snowmelt manually. If you're going to blade an area and get it to where a campus is open, it takes a lot of time and a lot of manpower to cover a large area quickly. Snowmelt systems are just natural solutions for those. The other thing with collegiate environments that we see is the energy source, the power plant that drives the snowmelt. A lot of large schools will have their own industrial complex, so to speak. It's either a steam generator, they're coal burning, they're any number of large energy producers that are heating all the buildings, and they're delivering energy to multiple facilities. So to tap into that is a natural extension of what they're already presenting. And snowmelt systems are not load heavy. Sure, when it snows, you're going to increase the load at that point, but it's not like we're trying to deliver that type of load 24/7. They're definitely point of use, and they can be managed very easily within a building automation system for those type of systems.
We had another comment come through here. Colin, it just says, we have SM all applications. that can only answer one. We are doing more schools now.
Oh, excellent. Excellent. That's good. And that's probably, we're seeing the same trend that we kind of talked about on the collegiate level. And just overall, people are trying to optimize safety and convenience. So that's good. Another one that came up, I see here, is military bases. Is another one that's a good avenue for the same reason. They usually have the industrial infrastructure to handle the addition of a snowmelt system pretty easily. Any other questions, Greg, at this point?
Nope, good for now.
Okay, awesome. All right, we'll move on here. One thing that we look at as what I would call as a soft benefit to snowmelt systems that is starting to get more awareness as people become more aware of snowmelt systems as a whole is the liability aspect of what snowmelt systems help eliminate. Snowmelt systems remove a big chunk of liability that impact especially the retail marketplace, and sometimes residential, but mostly retail, where you have somebody who slips and falls walking into your store or across your parking lot. That is an event that has solid dollars associated with it. And the cost of one or two of those types of incidents more than justifies the cost of a snowmelt system in most applications. In some areas, what we're also seeing, especially areas that are prone to heavy snowfall or ice production, is a lot of insurance companies are offering discounts for people who install a snowmelt system. And that is something that you would have to raise and ask your individual insurer if they offer that. But a lot of insurance companies are going that way because it is a preventive maintenance or preventive solution to eliminate the risk. And to offer a discount on your insurance is way less of a financial burden for the insurance company than it would be to pay out for a claim. So definitely something that we're seeing more and more of. Design. I want to take a few minutes and kind of run through some general design aspects for snowmelt systems and things that we need to think about and some things that may not always come to mind. One thing that I want to stress is as we go through this is one perspective on snow melt. Every time I do a snow melt design, my questions change, my outcomes change. I'm always looking at what is the optimum goal of the snow melt. What is the customer needs? What are the customer's needs? What are they looking to achieve? What are the construction profiles and parameters that I'm having to deal with? And at the end, almost all the time, no two snow melt designs come out the same. There's always something that's going to drive a variance. It can be controls, it can be operational needs, it could be heat source options. There's a lot of things that change my designs. And there are also a lot of factors that people will take into account based on what their goals are and what their perspectives are. We'll kind of highlight some of those here, but if you end up with two different designs, that doesn't mean one's right and one's wrong. It means you have two different designs. And they both, ironically, will probably work just fine, depending upon what your attributes are. So, a couple things to look at. We have options out there from a snow melt perspective. We can do an electric system. We can do a hydronic system. There are some design elements from a performance standpoint that are referred to as an area-free ratio. Area-free ratio is basically referring to how well am I keeping up with the snowfall as it snows. If I am dealing with a residence and their goal is just to not have to shovel snow, and they don't care if it takes 3 hours or 6, I'm probably going to design for a lower performance curve than if I'm dealing with a hospital where their concern is they don't want anything on the ground. They want to make sure that that area is free of snow and ice all the time because you have patients that are walking in or being transported in and they just can't afford the risk. Control strategy. Control strategies are going to influence performance. They're going to influence operational response. They're going to influence mechanical design. It's going to influence a lot of things. And the control strategy can feed your mechanical design as well as the mechanical design can feed the control strategy. They interlock a little bit. Insulation, drainage. Drainage is one of those things that most of the time people don't think of, ironically. We just don't think about where the water's going to go. And most people say, oh, well, we have water accounted for because of summertime rains. We know where the water's going to go. In a snowmelt environment, that isn't always going to be the same profile. And the reason why is in springtime rain environment, if you look at a driveway, in theory, I have 4 sides of the driveway that can accept water runoff. The grass, the highway, a lot of different areas. In a snowmelt environment, I don't always have all 4 sides. I have a snowmelted driveway that has created a channel because now I have snow that's built up on the grass surfaces. I have snow that may be built up on the roadway because we're melting snow faster than the snowplows can remove snow from the road. That water is going to be funneled to some degree to that lowest point. And a lot of times we end up with needing more drainage solutions for snowmelt aspects than we do for summertime rains. It is always advised to think about drainage when we think about snowmelt systems. Surface materials, are we dealing with concrete, asphalt, brick pavers? What are we doing? Different floor coverings or different surface coverings will impact my design. The more restrictive floor coverings or surface coverings that we have, asphalt versus concrete, if it's more restrictive, more insulative, I'm going to require a higher water temp in my fluid channels. I may require tighter spacing on the pipe. If I have areas that are trouble spots within a given area, I may need to double up on the spacing. I've had areas where they've changed floor cover or surface covering materials within a given snowmelt. A section could be asphalt and a section could be brick pavers. Knowing those coverings will impact how I design my system. And then in the site conditions, what exactly am I snowmelting? Am I snowmelting for 12 inches of snowfall a day or 24 or 48? One thing to keep in mind is there is no absolute design for snowmelt. Any snowmelt system is an art and an act of best guess. And the reason why is it never snows the same way twice. we can go through and design our system for 12 inches of snowfall, and it gets 6 on a snowfall. Or next time we could have a really bad winter and we have 18. There's no way to absolutely predict what a winter is going to do, because it's going to change from event to event, and the density of the snow is going to change from event to event. What we look at is a method of trying to best guess the performance. And knowing that we get close, we have to then know, what does it mean to make up the difference? And 9 times out of 10, the variance will be with time. We design systems to perform within a couple of hours. In reality, you could be plus or minus 30 minutes, plus or minus an hour, depending upon that snow condition that we're talking about. Okay, electric versus hydronic. First off, there isn't a better, best scenario. Both solutions work, and they both have their advantages depending upon the needs of the customer and the application. In general, electric snowmelt systems are ideal for smaller areas. Generally speaking, anything below 1,500 square feet will be ideal for an electric system, and that's for a couple of reasons. One, material cost. Cost per square foot for the actual material needed to run the system is going to be less on electric. Why is that? I don't need a boiler room. I don't need a boiler. I don't need circulators. I don't need piping and manifolds and glycol and all these other things that I need for a hydronic system. That cost, that mechanical room footprint and cost, is amplified on a small area. It just doesn't get distributed very well. So my cost per square foot will be better on electric systems for small areas. Conversely, larger areas will tend to be a better influence on hydronic systems, cost-wise. That doesn't mean I can't do a large area electrically. We have done large snowmelts electrically. We just did a casino that was over 9,000 square feet. Why? Because it was convenient. In order for them to have put in a hydronic system, they had to figure out a way to run physical piping from the boiler room inside the casino out to the snowmelt areas. That meant disruption of the casino floor. It meant disruption of sidewalks. It meant disruption of a lot of things that they didn't want to have to deal with. But the casino had power everywhere. You walk around a casino and there's power on every corner of the building. You know, there's parking lamps and lights in the parking area that they could tie into. There was power abundantly everywhere, that they were able to put in an electric snowmelt system without disrupting the flow of the casino itself. So a lot of times the needs are not necessarily which one's more cost effective by the material, but what do I need to make the project more cost effective? Couple of advantages here. Generally, lower cost installation we talked about. Less warm-up time, system responds faster. I'm going to add that with a grain of salt. Generally, the warm-up time will probably be about the same. What will drive the variance, though, is wire temp versus water temp. You're going to have a performance curve variance because the wire is going to be a fixed wire temp. Hydronic systems are going to have a variable water temp. And so you can change and tweak some of your performance variables easier on a hydronic system than you can on an electric system. So that one's kind of a grain of salt type of thing.
Hey, Coach, we had another question. Another question come through here. Yep. What is the rule of thumb break-even size of electrical versus hydronic if you already have a boiler on site?
Ooh, good question. You know, I'd probably say it's under 1,000 square feet. It'd probably 750 to 1,000 would be my guess.
Yeah, that'd be my guess.
Fuel cost is kind of a locked in on electric. Obviously, you're stuck with electricity, so whatever your fuel or cost of electricity is going to be it. Whereas on a hydronic system, you can choose maybe an alternative fuel source, whether it's oil system or natural gas or wood-fired, or you can maybe do a X to water heat exchanger Talking about the grocery stores, for example, we will do grocery stores where they will tie into the freezer systems in the food aisles and throw a heat exchanger on the freezers and take that extracted heat off the freezers and dump it out to the walkway into the entranceway. It's free heat. They were losing that heat anyhow to the atmosphere. Capture it, reclaim it. The only cost that they have to keep a nice free entrance is the cost to run the circulator. You know, why not? So there's some flexibility there in the hydronic system to maybe do some different things. Okay, energy load. When we do a design for a snowmelt system, we are looking at various aspects of the snowmelt profile. And that profile is looking at a couple different things. The actual melting of the snow as we clear areas, and you have drifting effect, and so you don't actually have 6 inches of snow across the entire area. You have 4 inches here, 8 inches here, 5 inches here. It's variable based on wind and drift. As areas melt, you get clearing that is uneven. And so you'll end up with evaporative losses that will drive an imbalance. You're going to end up with atmospheric losses and a chimney effect that drive imbalances. And then, of course, as the area clears, you have wind and black body effect up to the sky that drive a loss factor as well. Of those, and you have back and edge loss as well that goes into the ground. Of those variables, melting is probably the key factor. The energy required to melt or change snow or ice into a liquid is the key driver. It's probably 90% of the load that you're looking at for the most part. But we do take into account all of them so we have an optimized design. The free area ratio that we mentioned before, this is kind of an idea of what we're looking for here as far as performance. A free area of 0 is going to be your residential. Those are areas that I'm going to allow for some, mainly a little bit of buildup. It's not going to remain clear all the time. An area of 0.5 is partial. I'm going to keep up with most of it, but there will still be some buildup as the system runs. And then, of course, I have a free area of 1 where there is no accumulation. These are hospitals. These are handicap access ramps. These are critical areas that cannot have any buildup at all. And as we go up the scale, as we move from a 0 to a 1, our design load will go up. We are needing to pump more BTUs into a class 1 than we are into a 0 because we have to make sure that we keep up with any snow or precipitation that happens as it occurs. Okay, some insulation variables to look at. And insulation, I'm going to go through an example here after I clear the slide of some insulation considerations. There are a wide range of reasons to insulate a snowmelt system and likewise reasons not to. They are all valid. It depends upon what your goal is for the design of the system. And this is one of those areas where if you talk to 10 people, you'll get 10 different answers, and they're all going to be right. And there are some people who will be very emotionally driven by this factor and feel that there's only one way to do it. The best thing that I can do and recommend to each of you is to understand all the perspectives so that you can better design a system for the customer's needs. As far as insulation goes, a couple things to look at is the intended operation of the snowmelt system itself. Is it a walkway, or is the only thing I'm dealing with is foot traffic? Is it something that's going under vehicular traffic? The heavier the loads are going to drive what type of insulation I can and cannot use. What I don't want to do is use an insulation that can compress. I want to make sure that my insulation is going to withstand the vehicular load or whatever dynamic loading there is. Sometimes that's going to be a board insulation. A Dow blue board, for example, a 1-inch blue board can handle 25 psi compression. A 2-inch blue board can handle 100 psi compression. That's going to drive, the loading is going to drive what type of insulation that I look at. Is it a suspended slab, parking garage, walkway between buildings? Maybe I can't use a board insulation, but I have to use a foam insulation or spray-on insulation. What is it that I'm trying to insulate against? The ground or another wind-exposed surface? If I'm insulating, I either insulate the whole area or I don't. If I insulate portions of an area, you will get performance variables that you cannot control because of a couple of things that we'll get into here in a minute. Also, what is underneath my slab? Am I dealing with rock levels? Am I dealing with a hard surface, a hard ground that has stone that's going to conduct heat away very rapidly? Am I dealing with high water tables that are going to rob the mass of heat that I want to try and isolate from? In these cases, I want to insulate as well as I can to isolate the snowmelt from these loss areas. However, there is a performance thing that we want to look at too. Adding insulation will definitely decrease the response time in the sense that the system will come up to temperature faster. The more I isolate that mass, the faster it will respond. If I don't insulate at all, there is a certain percentage of heat that is going to go into the ground on startup. And it will basically be a split. It'll be 50% up, 50% down. As the ground mass comes up to temperature, my delta T between the snowmelt mass and the ground becomes less and less. As the ground temperature becomes warmer, I lose less heat to it. More and more energy goes up into the snowmelt surface. So eventually, after about a half hour to an hour of operation, almost all of my heat delivery to the snowmelt is going into melting snow. So I do have a response time that goes into the system if I don't use insulation. Conversely, if I use insulation, my system comes up to temperature faster, but it will also cool faster. And if I have an area that has poor drainage, that has the ability to retain water on the surface after the melting system has stopped, and it is a system that will cool faster, I have the potential of creating black ice because my system cooled too quick. It's the one thing that I've tried to prevent. The advantage to having that mass underneath the snowmelt system at this point without insulation is it will give me a coasting effect that will allow the mass to stay warmer longer after runtime. So I run the potential of eliminating that black ice effect post-run. There's a little give and take.
Hey, Colin, we had another question come through right now. How many feet per second flow rate would you design a typical hydronic system for? What is the best piping material?
Feet per second. That's a good one. I don't know the feet per second right offhand, but generally speaking, from a load standpoint, you're probably going to be between 120 to 150 BTUs a square foot, pure swag, on what my load is going to be. Your flow rate's going to be dependent now upon, am I at 6, 9, or 12 inches on center? The tighter the spacing, the lower my flow rate needs to be to deliver the same amount of BTUs. Water temp, you're going to be about 120 degrees, give or take. Now, that's going to vary greatly depending upon the actual snowmelt material, asphalt versus concrete versus whatever. But about 120, 150 BTUs a square foot is my range. Hopefully that answers the question.
Yes, thank you.
Okay. So what the next example that I want to look at real quick is choosing insulation strictly based on cost and the assumption that by using insulation, I'm saving money from a performance standpoint. And if we run the numbers and we look at just a basic 1,000 square foot area, because the numbers work out and I can do the math, an estimated cost, national average for a therm of heat of BTUs is about $1 a therm for natural gas. The cost for insulation, 1-inch Dow Blue Board, is about 75 cents a square foot. To insulate that 1,000 square foot area is going to cost me about $750 to insulate. If I look at cost savings from a loading standpoint, if I were to run with insulation 125 BTUs a square foot and without insulation at 150 BTUs a square foot, I'm about 25 BTUs variance. You look at that, assuming an average runtime of 4 hours, it's about a therm per runtime, or about $1 variance per snow event, which is about $10 a year on cost savings. So it'd take me about 75 years to return that investment. If I doubled my savings and I said I had 50 BTUs a square foot variance, I'd still be at 37 and a half years. So if I'm looking at strictly as I'm saving money from a runtime standpoint, I may or may not be doing that. That's something that we should look at. Performance factors, different deal. Responsivity, different deal. As Tracy mentioned earlier, protecting areas from the heat migration from the slab, i.e. into landscaping, into other elements that line a snowmelt area, different factor. Those all are valid reasons to insulate and insulate well. But just understand that it may not necessarily be a true hard dollar savings. Another way to look at this is that extra runtime of an hour per snow event. Run the same numbers and it comes out about the same. It really isn't saving me a lot of time and or dollars. Just something to think about. Different perspective, right, on what I'm doing from a design standpoint. And the reason why I bring this up is when you start looking at the cost on especially large snowmelt areas, insulation by itself becomes a huge factor on what the system cost is. And if I am looking to value engineer a system to create the best performing system at the most optimum cost, I don't always have to look at modifying the snowmelt system itself. There are other things that I can look at and recommend. Installation-wise, we want to install the system or the piping at least 2 to 4 inches down below the surface. I don't want to be any closer than 2 inches to the surface for structural reasons. I got to have room to float the aggregate and a whole bunch of other things. Typical pipe size is going to be usually 1/2 inch to 3/4, depending upon load, flow rate, pipe spacing, run length. The longer the run needs to be to cover the area, the larger the pipe diameter may need to be. No wider than 12 inches on center. If you were, and I don't care what the application is or the snow load, if you install pipe wider than 12 inches on the center, you will end up with a candy cane for a driveway. It will be striped, and you will never melt in between. It just isn't enough heat migration. Yes?
Yeah, another question come through. Sorry to interrupt.
No, you're good.
What would the glycol percentage in your loop, if you're dealing with different zones fed from a common glycol heat exchanger, what is the good practice for having the fluid properly circulated in all zones loops?
Okay, a couple things about glycol. Very good question. Generally speaking with glycol, we design systems or recommended systems be designed with 50% glycol. The range of glycol percentage is between 30 and 70%. And we shoot 50 because it's right in the middle. For one, it's an easy ratio to remember. Anything less than 30% can create some corrosion issues. There aren't enough inhibitors in the glycol mixture to offset the acidity or the pH of the glycol itself. There aren't enough inhibitors to offset potential microbial growth, and you end up with bacterial blooms. There's a lot of things that go into it, then your system balance is off less than 30%. Anything over 70%, you're not going to be able to pump it. It's too thick. It's way too viscous, and you're not going to move the fluid. So 50% is about the right ratio to shoot for. A couple things to keep in mind is make sure that the glycol chosen is what we need for the system, in the sense of a lot of glycols now are formulated for the heat source, whether it's a cast iron boiler, copper fin tube boiler, stainless steel, the list goes on and on. There are different inhibitors in each of those that are compatible with the heat source. Also be aware of some glycols come pre-mixed. You can buy glycols that are mixed 95-5, 50-50, and anywhere in between, depending upon the inhibitors that are being added to the mix. If we use a glycol that is pre-mixed 50-50 and they mix it on site, guess what we have? We have 25% glycol, and it's not going to be enough. So you got to be careful with some of that. To check and make sure that you have the right glycol percentage on the system, you want to use what is referred to as a refractometer. This is a device that allows you to look at the fluid in the system, and all fluids will bend light, refract light, based on their freeze point. Doesn't matter if it's milk, water, Coca-Cola, or glycol, it will have a certain ratio of bend. And that's the only way to really check to see if you have the right percentage in your system, because your freeze point will be directly correlated to the mix ratio in your system. Beyond that, recommended to treat your glycol system, check it at least once a year for pH and proper inhibitors, and you probably have to do some treatment or flush and fill every 5 to 10 years, depending upon the use of the system.
We had another question come through. I think it was referring to your previous slide. Are you basing the operation on both temperature and snowfall?
Temperature, yeah. On the insulation question?
Yeah, I think that's when it came through.
Okay. Yeah, this example is just high-level gross numbers. As far as water temperature and snowfall amounts and runtime variables, those change everything, right? Again, that goes into what is the goal and purpose of our customers with a snowmelt system. How do they want to run the system? That goes into my evaluation. Generally speaking, water temperature is going to be driven by your covering. Is it concrete or brick pavers? That generally drives your water temperature more than anything else. The snowfall amount, whether it's 6 inches or 18 inches, will drive our BTUs more than anything else, along with response time. Couple other design factors to look at. One of the things that ASHRAE added to the calculation curve probably 10 years ago is trying to add a factor for that best guess. And when you look at the chart up here from ASHRAE, we have 75% up to 100%. What that means is, how sure am I that the conditions I'm designing for are going to happen X percent of the time? At a 98% time that's circled here, I'm saying that 98% of the snowfalls are going to be within the parameters that I've set forth in my design. So my design is going to be typically higher on load because I want to make sure that I hit those conditions 98% of the time. A 75% design window means, 1 out of 4 I'm going to hit it, or 3 out of 4 I'm going to hit it, 1 out of 4 I'm not. That's okay. I'm good with that. I'm going to typically design for a lower load because the factor I'm changing is not whether or not it's going to melt or not. It's whether or not it's going to melt in the time I want it to melt in. It's really more of a, is it going to happen in a 3-hour period or 6 or 7? And that's just how do I want to run my system. This example that's shown up here is based on a 5,000 square foot area, and it's kind of give you an idea of what the on-off runtime cost would be annualized. About $1,300 for natural gas and about $5,100 for electric, depending upon what your costs for utilities are. Idling. There's a couple of things to know about idling. Old school thought, new school thought. Idle systems were basically systems that ran all the time. And to quote my kids in the olden days, when we really didn't have good controls that could anticipate snowfall. So the only way to have a system ready to handle any type of condition that was thrown at it was to maintain temperature all the time. So these systems maintain a temperature anywhere between 30 to 32 degrees all winter long. This was your helipads. These were your hospitals. These were your areas that could not afford any sort of buildup. And those systems cost a lot to operate. The nice thing about today's systems are tied into the internet. We have Wi-Fi controls. We have smart controls that are tied into weather apps that have the ability to anticipate snowfall before it happens. So the controls will say, oh, weather app says, hey, snow's coming in 4 hours, I better turn on. And it will preemptively start the system before the snowfall comes, so we get the effect of an idle system without the cost of an idle system. So you kind of have to look at this one with a grain of salt as well. This is more based on a system that ran all the time. Payback on a snowmelt system versus mechanical snow removal. This is basically looking at what does it cost for equipment, labor, all that good stuff to physically remove snow. In some areas, you're dealing with having to pay to actually remove the snow because you have to have some place to dump it. A lot of areas won't allow you to dump snow just anywhere you want to. You have to take them to a treatment facility so that they can be treated, so you're not dumping debris into the waterways. All those things go into this cost analysis. Poll number 3. Greg, what do we got?
There you go.
We have, what is the most common snowfall or snowmelt size? What are you all looking at when you see a request for a snowmelt system? Are we talking large systems or more of the smaller type residential systems? And I promise I will start to talk faster. I get into this stuff and I get excited about snowmelt and I tend to drag on. So I will try to wrap this up as fast as I can. We have a couple more highlights to hit, and then we'll wrap up. All right, let's go ahead and close this out and see what kind of results we had. All right, kind of a 1,000 to 5,000 square foot area. I was kind of actually anticipating it to be a little bit higher than that, but that's interesting. Okay, cool. Controls. We have a wide range of controls that can be used. We have standalone controls that are isolated to just the snowmelt system itself. We have controls that can tie into BACnet, Modbus. There's a lot of different levels of control interface and awareness that we can look at based on our needs, based on whether we want to be able to remote monitor systems, remote access and turn on systems. Some of the controls that we look at have apps that tie into them, so you can look and remotely turn systems on from your phone. You can look and see what your run times have been. And that's kind of a good thing, too, in case you have something that goes down, fails in the system, and you want to just say, hey, has it ran this month? What is it on when it needs to be? Whatever the case may be. One thing that we don't recommend are manual on-off switches. You can do that. We can design a system that is a manual on, manual off. The problem is that you turn the system on at 10 o'clock at night when it's starting to snow, you go to bed, you forget about it. And then you go 5 days and realize, uh-oh, my snowmelt system's still running for 5 days. Not really good. So if you want a manual on, do some sort of automatic off. Timer, something that will automatically shut the system off after a pre-described period of time. Sensors, wide range of sensors. We have sensors that go in the slab that measure snowfall and precipitation and slab temperatures. These are great for actually being able to monitor the actual snowmelt pad itself. We also have pole mount sensors that go on a pole that can be mounted by the building. It can be mounted just about anywhere. It doesn't have to be in the snowmelt area itself. The assumption is if it's snowing in my driveway, it's going to be snowing in my backyard too. So I could put it just about anywhere. The advantage to these, or why do we look at both of these? Well, it kind of depends. There are a lot of reasons why I want to look at an aerial system. One could be the slab sensor in the snowmelt area was misplaced, and I need to run a different sensor. It could be that I had a split system and I only put one sensor in one area thinking that it would control the performance of multiple areas, and it didn't, so I want to add a secondary sensor. Like it or not, I have seen a lot of systems where they didn't put the sensor in at all. You have multiple people working on a job. You have the hydronic specialist that's putting down pipe. You have the concrete guy that's pouring the concrete. You may have the electrician that's running the sensor wire, and everybody thought somebody else was going to do it. And pretty soon you realize the concrete's poured and there's no sensor. I've seen sensor sockets installed with no conduit. I've seen conduit installed with no sensor socket. It goes, across the gambit. So sometimes it's just a matter of necessity. I need to have an ulterior way of getting the sensor in there. So pole mount sensors are a good way to do that. My mechanical setup in the boiler room is going to be driven sometimes by the control strategies. Sometimes my control strategy is going to be driven by the mechanical setup. Do I have the ability to control multiple zones? Do I want to control multiple zones? What am I using as my heat source? Is it a condensing boiler that I'm coming directly off of and I need to control the heat source itself? Am I coming off of a heat exchanger? Am I looking at some sort of modulating mixing device? And that can be a three-way or a four-way mix valve. It can be an injection pump mixing. A lot of different variables go into what am I doing to control the system. Those all go into what type of system do I want to use. What size of system do I have? Am I able to use a small wet rotor circulator, or am I going to a larger inline circulator that requires a contactor to start as opposed to the relays that are built into the control? That's going to add another layer of complexity to my electronics so that everything talks properly. Regardless of all that, there's a solution that will tie everything together and get the performance that we need. Generally speaking, snow melt controls are going to monitor not only snowfall amounts but also slab temperatures. We want to keep the slab at a certain temperature, obviously, to melt snow. Typically that's about 35 degrees. Snow melts at 32. Stressors in concrete slabs, very real thing to keep in mind. That's one of the reasons why we want to have at least 2 inches of the concrete above the pipe if it's a hydronic system. Generally speaking, a lot of times we'll hear people talk about thermally shocking concrete slabs. Hydronically, incredibly difficult to shock a system hydronically. And the reason why is system starts, the fluid in the system out in the slab 0 degrees, -10, -20. System starts moving, and that -10 degree water temperature is mixing with my boiler temp water, and I'm not sending 120 degree water out into the mass or 150. I'm sending 60. I'm sending 50 on startup until that return temp starts to slowly creep up, and within 5 or 10 minutes, now my supply temp starts to come up. It's very hard to shock a concrete slab hydronically. Take that into account with an electric system, though, and I can easily shock a system in an electric system because when I flip the switch on an electric gradient system, I am 120 degrees across the board. So our design on the wire that we use is about 120 to 125 degree wire temp. We're not getting up to the 150s or the 180s where you can see a condition of thermally shocking the system. But it is a phenomenon. Used to be very prevalent in the 40s and 50s when electric systems were very popular and had zero control. And you would see that happen a lot. In today's systems, not so much. Still good to be aware of what drives that and what causes thermal shocks. But the reality is you probably don't see it very often. Redundancy inside of the snow melt system. The larger the snow melt area, I highly recommend adding sensors whether you use them or not, for a couple reasons. One, you may not know the best place to put the sensor. In a very large area, you're going to have performance profiles that change. You could have areas that are impacted differently than what you anticipate. For example, we had a snow melt system that was designed several years ago that had a large parking area and then a walkway area. And the walkway area was actually shrouded and concealed by the building in the sense that it had more shadow time than the parking lot. And so it stayed colder longer and didn't have the solar gain effect. And so you ended up with an imbalance just because the system was running off the parking lot where the sensor was and not where the walkway was. So it may be advantageous to add sensors and to break your system up, whether you design or intended to run it as multiple zones or not. Large areas, you may want to have that flexibility down the road. Good example of this is maybe all of one project, 4 different areas, and you could have 4 distinct performance profiles based on solar gain, shadowing, drifted snow effect, point of use. You know, if you can break it out into multiple zones or multiple control points so that you get the performance that you're looking for. Because I may want to run the driveway more often than the sidewalk or the front walkway. Smart controls, kind of touched on this before, they're tied into the internet. A lot of them are now. We have Wi-Fi, we have weather apps, BACnet. Smart controls allow us to interface with what's going on more directly. Mechanically, a lot of snowmelt systems or mechanical systems can be designed specifically for the application. Again, whether it's using injection pump mixing, heat exchangers, if we need autofill systems for glycol feeders, all those things can be packaged into the mechanical solution. A lot of different sizes, a lot of different configurations. Like I said before, no 2 snowmelt systems will ever be the same. There's always going to be something that gets tweaked between the 2, and a lot of times it's the mechanical room that gets tweaked because any number of systems can have different heat sources. You may design the same snowmelt solution from the manifolds out, but the mechanical room is going to be dealing with condensing boilers, cast iron boilers, natural gas versus electric boilers, a lot of different variables that go into those. Piping options, wider range of options in the industry today. We have EPDM that can be used. It's an incredibly flexible pipe, usually freeze resistant, kink resistant, UV resistant. You can drive on it, walk on it, doesn't hurt the pipe. We have our standard that is PEX. And we have various options of PEX, from a standard EVOH on the outside to a PEX aluminum PEX where you have an aluminum core on the inside. And then we also have PERT that's cousin to PEX, performs the same, installs the same, all that good stuff. Different operations or different conditions on the job site might drive which pipe option is best, especially if you're dealing with a snowmelt system that has to shape or conform to various odd profiles, i.e. stairs. You may find an EPDM or a PEX aluminum PEX to conform to a stair profile easier or better than a standard PEX pipe may. Getting out to the snowmelt manifolds, most of the time snowmelt manifolds are going to be remotely mounted. They're going to be outside, exterior of the building and the heat source. We want to be able to have the ability to get heat from the heat source, i.e. inside the building, out to the manifold system with as little heat loss as possible. So what we look at there is some sort of pre-insulated piping system to minimize that ground loss, the heat loss to the ground. And then, of course, our manifold assemblies come in various shapes and sizes. You can deal with manifolds that are copper, manifolds that are stainless steel, brass, HDPE, a lot of different configurations based on the system, the application requirements. Thin purge assemblies, isolation ball valves for supply and return lines, balance valves can be added to these, flow indicators, all the good stuff. And finally, our last poll of the day, real quick, we have just want to see what type of tools you use or would like to use to design systems. If you're using a system already, let us know that. If you would like to see a new tool, or if you have a need, it'd be nice to have product X or a solution X, let us know that. We'll give you about 20, 30 seconds to kind of go through that for us. All right, we'll give it about 10 more seconds. I know this takes longer because you have to type it out, but in the interest of time. All right, let's go ahead and close this down.
Should be able to see the results now, Colin.
Okay.
Can you see them?
Well, I don't think anybody responded,
Okay.
so that's okay. It was a long shot. All right. Finally, a couple tools out there, though, just for awareness. There are some online tools that are available. There's a Selected tool by Watts that allows you to go out and do some quick down and dirty estimation for systems, snowmelt systems, a couple of valve systems. This is a solution that's always growing. New products are being added all the time. There's RadiantWorks for more detailed designs. There's LoopCAD for more detailed designs. A lot of the Radiant manufacturers have solutions that they use for designing systems. Some have more capabilities than others. Some are more flexible than others. Some are online, some are not. A lot of different solutions out there. This is one of many. They're fairly fast. The online solutions are fairly fast to use. They're intended to get a rapid response to kind of make sure that everybody's on the right track and that the system's design's heading in the right direction. Most of those type of solutions provide some sort of package specification, so product spec, system details, those sort of things.
Yeah, I'll just add there, if you want to click through to the selected page on watts.com, I put it in the chat window if anyone wanted to click see it.
Okay. There you go. That one. And that is our presentation. We'd like to open it up for more questions. If there are any questions that you'd like to have, be happy to stick around and answer those for you. If there are no questions, we would like to thank everybody for taking their time today to sit through this with us, and hopefully you learned a little bit. If there are any questions, yes.
We did have some good questions come through here.
Awesome.
I appreciate everyone sticking around. I want to address a few that came through. So the first one here is, where are the ASHRAE snowfall tables?
Where, in the sense of in the design software or just in general?
That's all the questions.
Okay. In general, they're, I believe, located, there's a snowmelt section in ASHRAE and there's a fundamental section in ASHRAE. They're located in the snowmelt section, chapter 52, I think. I'd have to look. But those tables are, they're generalized tables. One thing to keep in mind when you look at those tables out of ASHRAE, they're fixed under a certain condition. They're not dynamic at all. Obviously, they're a table. So they're looking at worst case. What we do, and almost everybody else that has a software solution, we're running the actual calculations, the actual equations that are taking in dynamic data such as snowfall amounts, ambient air temperature for your location, and some other factors, and we're deriving a snow load that is more accurate to your location. The tables are very generalized, and in fact, a lot of times the tables are heavy on loads. If you design around the ASHRAE table data, you're going to be safe. Hands down, it will work just fine. The flip to that is that generally speaking, it's going to be oversized to the point where it may or may not be the most efficient system because it's taken a lot of assumptions in case or in factor. So keep that in mind. But that's generally where those tables are located: fundamentals and the snowmelt section.
Okay. Another question here. Do you recommend a separate circular for each manifold, or where do you draw a line, or single pump versus multiple pumps?
Good question. Unfortunately, that can be just a personal preference. Me personally, I like to go separate circulators per zone. And the reason why I do is for a couple of reasons. One, especially on a snowmelt, it helps keep the circulator size down to a more reasonable, smaller wet rotor circulator size. If I grouped, especially on large systems, if I grouped all the zones together into one circulator delivery, that's going to get to be a very large circulator in a lot of cases, and it could get into three-phase motors pretty quick. The other thing is, by breaking it out into multiple circulators or control methods, if I have a circulator that goes down for whatever reason, and I have a 5-zone system, I'm not sacrificing the other 4 zones on performance. I can still run the other 4 snowmelt areas while I repair the one. If I had them all tied together, I'd lose the whole system. So depending upon the criticality of what I am doing will kind of drive that decision as well. I could do a single circulator with redundancy. That's an option. Hospitals do that a lot. Everything gets redundant on a hospital just because of the criticality of having systems run. You can do single circulator design with multiple returns and zone valves. That works okay, but I tend to be more of a circulator guy than a zone valve guy. And no right or wrong, it's just my preference.
We have a quick logistical question here. Is the recording going to be somewhere? The answer is yes. You'll receive an email with a link to the recording. I'll also send a link to our webpage with all our recorded webinars on there as well. So you can click on that just in a second here. But another question for you, Colin. Is there a snow melt system available for Revit with the engineering behind the design?
Not from us, no. What I have should be Revit compatible will be the manifolds and some of our enclosures, but that is the only thing that I have that is Revit compatible at this point in time. That may change as time progresses, but we don't do a lot with Revit in general right now.
Okay, and how does system performance change from snowfall to snowfall?
Generally, the only thing that's going to change is time. Snowfalls will either perform faster or slower based on the snow condition at that point, based on when the snow starts. So if the system is at 30 degrees and it starts snowing, it's going to take very little time for it to get to 32. But if it's at -10 when it starts snowing, or 10 degrees, or 0 degrees, or whatever the case is, and I have to get up to 32, that's going to be a time lag. So a lot of that's going to factor in mainly time. Once I get to 32, 35 degrees on the mass, it's going to melt, and it will continue to melt as long as the system runs. So that's really the biggest variable between snowfall to snowfall is runtime.
Okay. Sometimes you end up with water spillage and ice buildup while there's no snow. Is there a sensor for that, or it should be a combination of 2 or more sensors?
If you are in an area that is prone to that, I would look at slab sensors to try and maintain a slab temperature above 32 degrees or above whatever set point is deemed necessary for the application. Unfortunately, there isn't necessarily a good moisture sensor for that. We have the sensors that go with the controls that monitor moisture, but if it's not freezing right above the sensor, it may or may not be effective in controlling the system based on that. But for example, car washes, where that's a big deal on their aprons, they'll typically run more on just slab sensors than they will based on snowfall sensors because they're trying to maintain a slab temperature above 32 degrees.
All right, and does using a larger diameter pipe provide more snow melting capacity?
Trick question. Yes and no. It does not provide more heat. I will get the same amount of BTU delivery out of a 3/4 inch pipe as I do a 1/2 inch. What changes, though, is my pressure drop. The bigger the diameter of the pipe is, the lower my pressure drop for the run of length of pipe I have. So generally speaking, as my snow load goes up and my loading goes up, I need higher flow rates. Higher flow rates mean higher pressure drop. I could run a higher flow rate in a lower or smaller diameter pipe, but my pressure drop is going to get pretty high pretty fast. So I tend to go to a bigger diameter pipe simply from the mechanics of the circulator, not because of the heat delivery off the pipe. So in a way, yes, I get more BTUs out of a larger diameter pipe because I can move more flow, but not because I'm delivering more heat. Make sense?
Yes, thank you.
Yep.
And what kind of glycol should be used in a snow melt system?
Good glycol. You know, the type of glycol typically we're looking at is propylene glycol. Propylene glycol is generally considered food grade, so it's environmentally friendly. So if you spill it, you're not going to hurt anything. There are systems that can use ethylene glycol. Those are not environmentally friendly, and you have to be incredibly careful when you use those. It's not a problem for the snowmelt components. The pipe, the circulators, you know, the components that make up the mechanical aspect are okay with either one. Generally speaking, though, 95% of the systems out there anymore go propylene glycol because of the environmental factor. You don't have to worry about disposing of it, per se.
We have a few more questions here. What are some of the reasons why a snowmelt system should be considered?
You know, for me, it's going to be, what am I trying to do? Where am I? Sometimes it's safety. Sometimes it's convenience. Sometimes it's going to be a cost savings from an operational standpoint. A lot of things go into the snowmelt system depending upon what the application is. If I'm a homeowner, I'm looking at my system for different reasons than if I'm a hospital owner, and I'm looking at it for, you know, safety of patients or helicopters. Homeowners looking at it from the standpoint that I don't want to get up at midnight to shovel snow, you know, or whatever the case may be. A lot of those things are going to change my perspective on what's important. But those are some of the main ones. Convenience, time savings, safety, and overall cost to clear is going to be main drivers for me.
How often does the glycol need to be changed?
Depends upon how often it runs. Systems that run more consistently or more often throughout the year are going to require more maintenance. What we recommend is that you test your system at least annually. And I actually recommend twice. I recommend about a month before the snowmelt season starts and sometime after snowmelt season ends. And you get an idea of how the system is aging. And it will age somewhat just sitting there during the summer, although not much. But it gives you an idea that if you test it after the season's over, what you need to do next fall so you can kind of prep and get ready for things. But usually, if it runs moderately, you know, a dozen times a year, you're looking at probably every 10 years, a system needing to be flushed and refilled. You may need to add inhibitors to the system, though, more frequently, though. So maybe every 2 to 3 years may need inhibitors added to keep the pH and some other things in check. But actually, flush and fill is probably once every 10 years or so.
Okay. And how long will a snowmelt system last?
Generally speaking, mechanically on the pipe and manifolds that are out in the snowmelt itself, those components will generally outlast the driveway or the snowmelt body itself. Concrete slabs, 40 to 50 years is a given lifespan. Ironically, in the snowmelt system, because you're not using the chemicals, the salts, the additives, it will last longer because you're not chemically abrading the surface. So you could get 60 to 70 years out of it at that point. Asphalt systems, probably 20 years. And the reason why asphalt systems are different is because asphalt is not a solid. It's a liquid. It's always moving. And you'll see driveways, you'll see parking lots. After about 2 to 3 years, they have potholes. They've kind of flowed and settled. And what do? They come through and they do a cap on top of that. So every 3 to 5 years, they're capping the top of the asphalt. I'm just adding more and more restrictive material to my asphalt, which means it's harder and harder for me to melt snow. So those systems will see a decline in performance over time. Doesn't mean that the system won't still function. It just means your performance is going to vary the longer it runs. Mechanically speaking, circulators, boilers, that type of stuff, you know, depends upon a lot of factors, but 20 years is probably a good estimate for mechanical components before they need to be updated, swapped out, something. A lot of that depends on how well I keep up my fluid, right? If I allow the system fluid to go out of whack on the pH, it'll become corrosive and it'll attack my mechanical faster and sooner, so I'll have to do more maintenance on them. If I keep the fluid in check, my mechanical lasts longer. There's a trade-off.
And is there an application type which cannot be snow melted?
Technically, no, but there are definitely considerations that we have to look at when we start getting into more of the unique stuff. Concrete slabs, 4-inch, 6-inch concrete slab for a residential driveway, not a problem. We'll melt those all day long. Commercial applications for an airport where I'm dealing with 18 to 24-inch slabs, yeah, now we got to look at some stuff. And the variance there is it's critical that we keep the tubing within that 2 to 4 inches from the surface. We start getting into a deeper variance and we start getting into that 12 to 18 inches down, it won't work. There's too much material above the pipe to get the surface to melting conditions. So my installation becomes critical on the application. The only time I've ever run into issues in performance is every once in a while you'll get a custom area that is using a really thick stone. It's a 6 to 8 inch stone paver, and the pipe is going to be in the sand bed below it, so I'm going to be 8 to 12 inches down. Again, it's going to be tough to be able to melt that effectively because I'm so far from the melted surface. Otherwise, no. Generally, anything that's a standard construction profile is not a problem.
Okay, great. Thank you, Colin. Those are all the questions we have. So I just want to say thank you for everyone who joined us today, and thanks for sticking around. I know we're way over here, but we appreciate your engagement in this webinar. Also, again, just to let you know, a recording of this presentation will be emailed to you along with that CEU credit as well. If you have any more logistical type questions, you can direct them at me at gregory.jackman@wattswater.com. And for any technical and topic related questions, you can reach out to Colin at colin.marshall@wattswater.com. Also, once again, once this WebEx ends, it'll bring you to a page where you can choose to sign up for our next webinar. It's going to be on August 28th on Legionella and Smart and Safe hot water solutions. You could also visit our snow melting page to learn more. You can click through to our online configurator, select it that Colin was talking about. And you could also visit our on-demand webcast page that I sent the link to in the chat window earlier, where you can watch all the recordings of all our past webinars, and you can take quizzes to earn more AFB-CEU credits. So thank you again, everyone, for joining us today, and enjoy the rest of your week.
Thank you, guys.